Hello, I'm Bram Desmet with Flanders Scientific, and in this tutorial we are going to review calibrating the FSI XM310K with Light Illusion's LightSpace CMS. Other XM series monitors can be calibrated in a similar fashion, but make sure to follow specific guides and information for the monitor you intend to calibrate, as some procedures or recommended practices may vary by model. To start, we're going to go to the color menu on the monitor to make sure our settings are set up appropriately for the calibration we intend to perform. We want to verify that the color system is set to LightSpace, as we will be calibrating with LightSpace CMS. Next, we will set the range to match the range of our test pattern generator. In this case, we'll be calibrating with DaVinci Resolve as our test pattern generator, and we will be calibrating in video range, so we will select video range on the monitor. Then from the gamut selection, we will select the memory position we are planning on saving LUTs to. In this case, we'll be calibrating for Rec 709, so we will set the gamut option on the monitor to the BT709 memory position. Next is an important consideration regarding the luminance selection. The XM310K can operate in either a static backlight mode or a dynamic backlight mode. The dynamic or modulated backlight mode will give us the greatest contrast ratio, and it is our assumption that most users will utilize the XM310K in this way the majority of the time. However, for some applications, like mimicking standard LCD contrast ratio performance, it may be useful to use the monitor in a static backlight mode configuration. We'll start by calibrating the monitor in the static backlight configuration, then we'll show calibration in dynamic mode. By setting the luminance mode selection to 100, the monitor will be configured for an SDR-appropriate static backlight peak luminance of approximately 100 nits. The custom selection can also be used here in combination with the luminance custom slider to increase or decrease the peak luminance as you see fit. In the static configuration, we can leave temperature and EOTF set to default. So next we will open LightSpace CMS and connect to the monitor by selecting the File, Upload menu option. Then from the drop-down list we will select XM. In this dialog window we will type in the IP address of the monitor, which can be found on the monitor system menu. So here if we look at the system menu on the monitor, we can see that the IP address is 10.1.10.14. So we will type that in here, then we will select 1D plus 3D, and we will select memory position BT709. And then we will want to ensure that null cube is checked, which in this case it automatically will be because we have no LUT active in the background in LightSpace. Then we will press upload, and what this is doing is loading unity or null cubes to the front 1D and 3D LUT positions. We then want to make sure we do the same thing for the back 1D LUT portion, because in static backlight mode there are 3 calibration LUT positions per memory slot on the monitor: the front 1D, the 3D, and the back 1D. Now we'll hit upload, and we can see that this LUT uploaded successfully as well. We now know that we have unity LUTs in all 3 positions, so we are starting from a neutral, uncalibrated, and native wide gamut place on the monitor ahead of profiling the display. The next step is to connect our test pattern generator. In this case, we'll be controlling Resolve as our test pattern generator from LightSpace. To give LightSpace control over Resolve, we will first select the Network Manager icon in LightSpace and then click Enable. Now we'll open Resolve and ensure that there is media on our timeline. If you do not have media on your timeline, Resolve will not allow you to connect to LightSpace. As a reminder, our current Resolve project is also set up to video range to match the video range settings selected on the monitor. If you're doing a full range calibration, simply ensure that both the monitor and Resolve are set up for full range. Now we'll select the Color tab, and from the Workspace menu, select Monitor Calibration, LightSpace. A dialog will open requesting an IP address. Type in the IP address from LightSpace noted earlier, and then press Connect. It is important not to press Return or close this dialog window, as that will terminate your connection and will not work with LightSpace as a TPG, so make sure that you leave this dialog window open in Resolve. Now we'll return to LightSpace and click on the Calibration Interface icon. For larger display profiles, we could also click on the Display Characterization icon, which allows for larger volumetric profiles. But because the XM310K is a very linear display and we are calibrating for a fairly simple Rec 709 target, a simple quick profile from the calibration interface will work just fine. If opening the calibration interface for the first time, we may get a probe-specific pop-up dialog. In this case, we are connected with the CR100. So we press OK. Now it's going to ask us to point the probe at a bright patch on screen. This request is specific to the CR100. Depending on the probe you're using, you may get no prompt or a different prompt. As you can see at the moment, the screen is only showing black, so we'll simply cancel this prompt for now. Then move over to the sliders here and move them to generate a bright patch. You'll notice that if I'm connected successfully to Resolve as my TPG, that the test patch shown on the monitor will mirror the test patch color shown here in LightSpace. Once I've done that, I can now go to the options here, and I can ensure that the CR100 is using an XM310K specific matrix. If you don't have an appropriate matrix for the XM310K, you can either create one using a spectroradiometer as a reference, or you can send your probe to us and we can create an XM310K matrix for you using one of our reference spectroradiometers. Next, we're going to make sure our extra delay is set to about 0.75 seconds just to play it safe and avoid any out-of-sync readings between TPG and probe reads. And then we're going to hit probe calibration. Now that we actually have a bright test patch on screen, we'll hit OK. This will take just a moment as it syncs to the display. Then once you get the frequency sync done dialog, you can hit OK, then press OK again, and we are now ready to profile. So at this point, we're going to select the profile option shown here and select the type of quick profile option we would like to use. We're calibrating for the back 1D LUT position first to establish a neutral white point in EOTF. So in this case, we're going to use a gray only profile, which takes numerous readings along the grayscale axis for us, providing ample data for a good white balance calibration of the display. It is important to note that if you plan on using the back 1D LUT position as part of a calibration process, that you always calibrate for the back 1D LUT position first. Now with gray only large selected, we can select start, and we're going to give our profile an easy to find name. In this case, I'll call this XM310K Unity All, and now we can start our profiling process. LightSpace will now automatically generate a series of RGB triplets, which are communicated to resolve and displayed on the screen. As the test patch is advanced, LightSpace will automatically take readings with the CR100 and log that data in this quick profile. So we'll give this a few moments to complete, and then build our back 1D LUT. Now you don't have to build a back 1D LUT. The calibration could be performed using just a 3D LUT by itself. But generally speaking, the back 1D LUT is helpful in that it provides a neutral white balance in EOTF starting point ahead of profiling for the 3D LUT, thereby limiting the 3D LUT's responsibility primarily to volumetric control of the display's color volume. So now that our display profile is complete, we can exit the calibration interface, and our next step is to select the color space conversion icon. From the color space conversion window, in this source dialog, we're going to select the target color space we want to calibrate for. In this case, Rec 709, so we'll select the Rec 709 option. Once selected, you can see that the XY chromaticity values for the primaries in white are automatically filled out appropriately, along with a default EOTF selection, in this case, Gamma 2.4. Then for the destination, the way I find it helpful to think about this is the location where your LUTs will live, in this case on the display, so we will select the display profile we just performed. That will be in our drop-down list here, and we call that profile XM310K Unity All, so we'll look for that profile and select it. Then we'll give our LUT a name, in this case Back 1D Rec 709, and then we'll press Create New to generate the LUT. Once generated, I can go back to File, Upload. Again, we have the XM series listed, the IP address of the monitor, we have the back 1D LUT position selected, we have the 709 memory position active, so these settings are all correct, but we want to make sure that the null cube option is now unchecked so that the LUT active in the background is uploaded to the display. Again, because we have just back 1D LUT selected, only the 1D LUT portion of this LUT will be uploaded into the monitor. Then we hit upload and we'll see a prompt telling us the upload was successful. Now we can run the profile necessary for creating our 3D LUT by returning to the calibration interface, selecting profile once again, and in this case we're just going to select gray only, which will give us primary readings and a short series of grayscale readings. Then we will press start. We're going to call this profile XM310K back 1D active, then we'll select OK, and again this will take a number of readings and log that into a quick profile from which we can build our 3D lookup table. Now as mentioned, you can do a larger display characterization and take a lot more volumetric readings, but because this is quite a linear display device and because we are calibrating for a fairly simple Rec 709 target, that is likely overkill. Doing a quick profile-based calibration like this is a good first step to see if a larger display characterization may actually be worth your time, and it is also a great way to ensure that all of your equipment is hooked up correctly and performing as expected before starting in on a prolonged characterization. We can now hit close and return to the color space conversion window, and this time we are going to build the volumetric 3D lookup table that will take us from the monitor's native wide gamut down to the Rec 709 target. So again, we are going to select the Rec 709 option in the source dialog. In this destination dialog, we're going to select the profile we just performed, which we named XM310K back 1D active. We're going to call this XM310K 3D, and then we're going to select Create New. That's now complete, and we can see that this conversion is 100% within target. We can actually take a look at the 3D lookup table now, and now we can select File, Upload. Again, we verify we have the correct device and IP address setting listed, and we're going to select the 1D plus 3D option, and then select Upload for the BT709 position. Now, it's important to note here I could just select 3D only. We of course already have that back 1D active, and choosing 3D only will work just fine, but if I select 1D plus 3D, that 1D LUT component of the 3D LUT will be extracted and uploaded separately into the front 1D LUT position. The front 1D LUT position on the XM310K is a 4096 entry point 1D LUT, so this gives us more granularity than we would have with the 3D LUT only. So we go ahead and do 1D plus 3D, press upload, and then we'll see that both LUTs are uploaded to the monitor successfully. We can now close this upload dialog and we can verify our results. So from the calibration interface, I'm going to select memory colors with secondaries as my verification, both because these colors are ones we care about like earth tones and skin tones, and because it is a separate set of data readings from the ones just used for calibration, so a more thorough way to verify our calibration rather than simply reading the same values as before. We're now going to press Start, give our validation profile a name, and then press OK. This will again generate a wide variety of test patches, and once complete, we will review the results to see how good our calibration is on this display. So now that our verification is complete, we can hit OK, and as we can see, our color gamut coverage is excellent. We could also go to our gamut coverage and see that it looks pretty spot on. RGB balance looks quite good. We can look at our delta for white balance, which also looks great. And then delta E distribution really tells us the complete story, and what we're looking for here is a very left-weighted graph. What this tells us is the percentage of delta E values that are between 0 and, for example, 0.5. And we see that depending on the delta E metric used, that is anywhere from 65 to 90+% of readings. Then not much of anything really over 1 or 1.5, so a very good calibration that was done very quickly. Again, we could do a much larger display characterization, and there's no real harm in that, but the significantly longer investment of time would likely only give us marginally, if at all, better results in this particular scenario. However, those larger display characterizations can certainly be much more useful when targeting more complex targets like PQ, or when dealing with less linear displays. Now that we've shown how to perform the calibration in static backlight mode, we'll take a look at how a dynamic backlight calibration differs. Returning to the monitor menu, we will go to the luminance selection and change this from our previous static selection of 100 to dynamic. In dynamic mode, the peak luminance of the display and their underlying EOTF behavior will be governed by the gamut and EOTF selections on the monitor. For example, if we select Rec 709 and Gamma 2.4, we'll get a peak luminance around 100 nits and a gamma around 2.4. These baseline selections are pre-calibrated as part of the closed-looped auto-cal process described in the first video of this series. One additional important consideration is to ensure that the optimized modulation mode is set to peak on the video menu before you perform your calibration. This will help to ensure the most accurate representation of code values to luminance output on the display while in dynamic mode. Once we've selected our baseline settings, we go to the File, Upload menu to again load Unity LUTs to the display before profiling. We will select 1D plus 3D to load Unity LUTs to the front 1D and 3D LUT positions. Verify null cube is selected, and then press Upload. Unlike the static backlight mode, we do not need to repeat this process for the back 1D LUT, as that is bypassed and replaced by the menu settings you selected after switching into dynamic mode. To profile our display, we can again either do a quick profile from the calibration interface or perform a large display characterization. Again, because we are simply calibrating for Rec 709 and the display is quite linear in its behavior, we'll just perform a quick calibration. At this point, the process mirrors the procedure used previously, so we'll give our quick profile a name, let it run, and then once complete, move to the color space conversion dialog. From this window, we'll select Rec 709 as our target, select the profile we just performed as our destination, and then create the lookup table. Once created, we'll return to the Upload dialog, uncheck null cube so that our active LUT is loaded, verify we have 1D plus 3D selected, and then press Upload. With the LUTs now successfully loaded, we can once again verify our result. As you can see, we retain a very accurate calibration result, but unlike the static backlight calibration, we have a significantly higher contrast ratio response on the display now. We hope this video has been helpful in showing how you can calibrate the XM310K with LightSpace in both static and dynamic backlight operation modes. If you have any questions on calibrating this or other FSI monitors, please reach out to our support team at support@flandersscientific.com. Thank you.